This is Euclid Book 10, proposition number 22. Here is the illustration. The square on a medial straight line, if applied to a rational straight line, produces as breadth a straight line rational and incommensurable in length with that to which it's applied. Alright. Let A be medial and CB be rational. Okay, so we have this line that's medial and CB, which is rational. That line length is rational. Okay? And let a rectangular area BD equal the square on A be applied to BC, producing CD as its breadth. Okay, what does that mean? That means if we drew a physical square and all four sides of that physical square was equal in length to A, the area contained in that would be the same area contained in this. Okay? And the breadth here is CD. So now we have BC, we have BC, we have CD, and we have CD. And the area in here is the same amount of area as what would be if we took this line, formed it into a square, and measured its area. So they're going to have the same area. Okay? I say that CD is rational and incommensurable in length with CB. So the first thing they're going to try to prove is that CD is rational. The second thing they're going to try to prove is that the length of CD is irrational. That the length of CD is incommensurable with CB. That's what we're going to try to prove. For since A is medial, the square on it is equal to a rectangular area contained by rational straight lines commensurable with square only, which happens to be Euclid Book 10, proposition number 21, which we covered in the last proof. Okay. Let the square on it be equal to GF. Okay. So the area, the square area in A is the same square area you're going to find in here. Okay? But the square on it is also equal to BD. Therefore, BD is equal to GF. So that means the area you'll find in here is the same amount of area you're going to find in here. Okay. But it is also equal angular with it. And in equal and equal angular parallelograms, the sides about the equal angles are reciprocally proportional. And this is by Euclid Book 6, proposition number 14. Therefore, proportionally, okay, as BC is to EG, so is EF to CD. EF's to CD. Alright. Therefore, also, as the square on BC is to the square on EG, so let's say we squared this, and we also squared this, okay? So is the square on EF, so let's say we square that, is to the square on CD. So in other words, this squared over this squared equals this squared over this squared. Well, that's by Euclid Book 6, proposition number 22. But the square on CB is commensurable with the square on EG. For each of these straight lines is rational. Okay? So, if we squared this and we squared this, those lengths, they would be commensurable. And therefore, they're rational. Therefore, the square on EF is also commensurable with the square on CD. This square is commensurable with this. And this is by Euclid Book 10, proposition number 11. But the square on EF is rational. Therefore, the square on CD is also rational. And this is by Euclid Book 10, definition number 4. Therefore, CD is rational. Okay? So now we're going to say that this length is rational. Okay? And since EF is incommensurable with the length with EG, okay, for they are commensurable in square only, so EF and EG are only commensurable in square. They're not commensurable in length. And as EF is to EG, so the square on EF to the rectangle FE and EG. Well, let me write this down for you because you're going to get confused here. Oops. Okay, according to the lemma, this is what you got. As EF is to EG, so as EF squared is to EF times EG. Okay, got that? Okay. Had to make sure I wrote it correctly. Therefore, the square on EF is incommensurable with the rectangle FE and EG. Okay, so what they're saying here is trying to think of a good way to say this. So if you were to make EF into a perfect square, in other words, all four sides have the length of EF, that area would be incommensurable with the area of the rectangle formed by EF and EG. That's what they're trying to say. And I'm going to bring this up real close so you can see that. Okay? Alright. And that's by Euclid Book 10, proposition number 11. But the square on CD is commensurable with the square on EF, for the straight lines are rational and square. Okay. So what we're saying here is, if you square the length of CD and you square the length of EF, then the areas contained by these two would be commensurable. They themselves probably wouldn't be, but their squares would be. That's what he's saying. Okay? And the rectangle DCCB, well, that's how the rectangle DCCB actually looks like. Okay? Is commensurable with the rectangle FEEG, for they are equal to the square on A. Well, now you got another rectangle. So these areas are commensurable, and the reason why is that they're commensurable with the square on A, which I've shown you how to draw already. Therefore, the square on CD is also incommensurable with the rectangle DC and CB. So, this is incommensurable with this. That's what Euclid is trying to say. Okay? And that's by Euclid Book 10, proposition number 13. But as the square on CD is to the rectangle DCCB, so is DC to CB. And that's by the lemma. So, as the square area here is to the square area here, okay, as this square area is to this square area, so is the length of this to the length of that. They're all in a proportion. Okay. Therefore, DC is incommensurable in length with CB, and this is by Euclid Book 10, proposition number 11. Okay. So these two lengths right here are incommensurable. You know what incommensurable means because you've watched all my other videos. Therefore, CD is rational and incommensurable in length with CB. So CD is rational, but it is also incommensurable in length with CB. And that's what Euclid was trying to say. Alright. I will tell you more in a future video, so stay tuned.